Welcome to the next lecture in electric circuit analysis. We were discussing the three-phase power, and we discussed that in three-phase circuits, the line and phase quantities are different. We need to measure the power as three-phase, and we have seen the formulas what are required to calculate the active power, the reactive power, apparent power, and the complex power. We have seen the power factor correction and the power triangle. But how to measure this power? So the focus of this lecture is to discuss the power measurement technique. Let us see the introduction first. We know that the wattmeter is the instrument which is used to measure the average or the real power in a single phase circuits. So in single phase network, we generally use wattmeter. We generally use wattmeter to measure the power. And the power when we measured for three-phase system, when it is a balanced system, we have seen that balanced system is the one which is having the same load or the impedances in all the three phases. So Z1 will be equal to Z2 will be equal to Z3. So when you have the same impedances in all the three phases, then that is known as the balanced system. And if the system is balanced, then we require only one wattmeter for measuring the three-phase power. The reason is the power in all the three phases will be equal, which is P1 is the first phase, P2 is the second phase, and P3 is the third phase, which is measuring the average or the real power. Then the total power is being given as 3 times the power in one of the phases. So it means if we measure the power in one phase and multiply it with 3, then we get the total phase power of the three-phase system. But this is only for the balanced system when the system is unbalanced. If the system is not balanced or unbalanced system, then power 1 will not be equal to power 2 in the second phase, and it will not be equal to power 3. So in that case, the total power will be the summation of the powers in the three phases. So we have to individually obtain these powers and we have to add it when the system is unbalanced. So if the system is unbalanced, then we require 2 or 3 single phase wattmeter. Now why 2 wattmeters we require to measure the three-phase power, that we are going to see, and how the connection is there, that also we will see. So 3 wattmeters are basically what I said just now, that if we add the power in the three phases individually, then we get the three-phase power for the entire network. But how this 2 wattmeter, it means one of the wattmeter is not required out of this 3 wattmeter. Then how it is possible that the power can be measured using this 2 wattmeter? So that is the focus of discussion in this lecture. We will also measure the power individually. Now, the connection of the wattmeter or the operation of the wattmeter is discussed in one of the lecture, and that video is already there. You can just see that how the wattmeter function, what are the voltage coil and the current coil of the wattmeter that is used to measure the voltage and the current. Because we know that power is basically the product of voltage into current for the single phase multiplied with the power factor cos phi. So it means that the voltage has to sense, the current has to sense, and the angle of the voltage and the current has to be sensed to obtain the power factor. So wattmeter physical connection using the voltage coil or the current coil has been discussed. Now, first we will see the three-phase power measurement using the 3 wattmeter method. So if the load is balanced or unbalanced, the load may be star or delta. So we have seen and discussed this star delta in very detailed in three-phase networks, like what is the relationship between the line voltage and the phase voltage for star connection, what is the relationship between line current and phase current for delta connection, that we have seen and studied for three-phase networks. Now the power measurement for three-phase system using 3 wattmeter is valid even the load is balanced or unbalanced, the load is star or delta. So we have three wattmeters, wattmeter 1, wattmeter 2 and wattmeter 3. Note these are single phase wattmeter. So it is being connected in one of the phases, either A, B or C. So A is connected with W1, B is connected with W2 and C is connected with W3. Now here you have the load. So load can be either balanced, unbalanced, it can be star or delta. It doesn't matter. Whatever may be the load, it doesn't matter. The wattmeter will measure the power corresponding to one of the phases A, B and C individually, and then we can add and find the total power. So these 3 wattmeter method of power measurement is well suited for power measurement in a 3-phase system where the power factor is constantly changing. So we know that power factor is basically depend upon the angle of the voltage and the current, which is equal to theta, and this theta depends upon what type of load you have, whether you have a resistive load, whether you have inductive load, or whether you have capacitive load, or the combination of that. So this load is constantly changing. So if the load is constantly changing, then in that case it is better you measure the power in individual phases one by one using this wattmeter, and then you measure and find the total power as the sum of P1 plus P2 plus P3 in all the 3 phases. Now note here there is a reference point O. This reference point is the common point, and these point can be arbitrarily selected. You can arbitrarily select this point O, and these function very important task in power measurement. Now let us see, if the network is star connected, then this O can be the neutral point. So if you have the star connected network, and here you have the neutral point. So these are the phases A, B and C, and the neutral point can be the common point, that is the reference point. But in delta you don't have the neutral. So when you talk about the delta connection, you don't have the neutral point. You have the 3 phases like this, A, B and C. So any point you can treat as O. You can treat this one as O, you can treat this one as O, or you can treat this one as O, or somewhere out also you can treat as O. That is the common reference point. Now there is a special case. Let us see, if O is connected to B. So we make some changes in the connection. This O point and B point are connected to each other, and there are 2 coils in wattmeter. One is the voltage coil and another is the current coil. This I have discussed in detail in the wattmeter physical connection. So you can know that the voltage coil will be in parallel and the current coil will be in series. So the voltage coil in wattmeter 2 will read 0. So if we see this wattmeter 2, when O is connected with B, it will read 0 reading, means no reading will come in the wattmeter. It will read 0 watt. So these advantage we are going to take for 3-phase measurement. So W2 being the wattmeter giving the 0 reading, it is not necessary, and 2 wattmeters are sufficient to measure the total 3-phase power. It means W1 and W3 will be useful and will be used to measure the total power, that is the average power in 3-phase network, where the W2 is basically showing 0 reading because we have connected the A with O. So the 2 wattmeter method is generally commonly used for 3-phase power measurement. I have told you that if the power factor is constantly changing, it is better to go with 3 wattmeter method. But when the load is balanced, then the angle between voltage and current will also not change, and hence the 2 wattmeter method will be mostly used. So now you can see that we are using only 2 wattmeter method, W1 and W2. 2 wattmeter we have used for 3 phases A, B and C, and there is no wattmeter connected to B phase. But precaution has to be taken. These 2 wattmeter must be properly connected in any 2 phases. You can see the common point is connected to the B phase only. So wattmeter W1 and W2, the common point is coming in B phase. The current coil of each wattmeter measures the line current. Note here, because we are measuring the 3-phase voltage and the current, so whatever the current is being measured, that is the line current. It is not the phase current. Even this wattmeter is basically single phase wattmeters. the respective voltage coil is connected between the line and the third line and measure the line voltage. So if you see the voltage coil, it is basically connected between the line and the common point between B. So the second wattmeter is also connected between the B, and this voltage is basically the line voltage. So we are basically measuring the line voltage and the line current using the 2-wattmeter method with proper connection of the voltage coil connecting at the phase B. The positive negative terminal, if you see here the positive negative terminal, it is shown all over in W1 and W2, that is being shown the polarity and the connection. So the voltage coil is connected to the line to which the corresponding current coil is connected. So this positive negative sign of the voltage coil and the current coil should be properly connected so that you measure the line voltage and the line current properly, and there is no need of the third wattmeter. The individual wattmeter are no longer read the power taken by any particular phase. So we cannot say now that W1 and W2 are measuring single phase power. So it is not correct. W1 and W2 are not measuring single phase power. The together cumulative sum or the average sum of W1 and W2 are measuring the total power of this three-phase system. So we are basically measuring the line voltage and the line current with respect to this wattmeter W1 and W2. So the total average power absorbed by the load, regardless of whether it is star or delta connected, balanced or unbalanced, now is being given by P1 plus P2, and this is the algebraic sum, because whatever the power we are measuring, that is the real power. So we are taking the algebraic sum of P1 plus P2 to find the total three-phase power. Let us validate that with the help of one example, and the derivation goes like this. So here you have three-phase load. So if you see the three-phase load, the three loads are connected and they are balanced. What is the meaning of balanced? The balanced means the load in individual phases are equal, which is equal to ZY angle theta. We are also considering that the source is of ABC sequence, means we will have voltage A first, then B, and then C. So it will be at minus 120 degree and it will be at plus 120 degree. So it will be at 0 degree. So we have ABC phase sequence, and we have connected two wattmeters W1 and W2 in phase A and phase C, and the common point is connected to phase B. So the current which is going in the phases IA, IB and IC. Using this current and the voltages, so the line voltage is VAB and VCB, which is measured between A and B and measured between C and B. So the voltage is leading the current by theta. If you note here, the impedance we are taking at plus theta, it means that the voltage is leading the current by theta and the power factor is basically cos theta. So the power factor will also be measured using 2-wattmeter method. Recall what discussion we have done in star connected network. So this is basically a star connected network. Line voltage is 30 degree ahead of the corresponding phase voltage. So when we say the line voltage, it is equal to √3 times the phase voltage. This is the magnitude, and it will be 30 degree ahead. So if this is for the phase A, the other phase B will be only changing the angle of 120 degree. So there will be no change in the magnitude, and the other phase C will be changing by another 120 degree between B and C. So this is the concept that we have discussed for the star connected system, and this concept will be useful here. So we can say that the total phase difference between the phase current IA, so the current which is measured is the phase current, and the line voltage VAB is 30 plus theta. So theta is the phase angle between voltage and the current, and 30 degree extra is coming because you have to deal with the line to phase. Hence, the power which is measured P1 and P2 in the 2 wattmeters P1 and P2 are basically the real of the complex power. So complex power is basically VI conjugate. So here we are using the line voltage and the current line current, and line current is equal to phase current because it is a star connected system. So we can say that the real of VAB IA conjugate will give me P1 and real of VCB IC conjugate will give me P2. And this is nothing but VAB IA cos theta plus 30 degree. Why we are saying this? Because the general formula is VI cos phi. This is the general formula. And this phi is nothing but theta plus 30 degree that we have. And this is the line voltage and this is the line current. So line voltage in phase, the line AB is VAB and the line current is equal to the phase current for a star connected system is basically equal to IA. So here we have taken IA, here we have taken IC, and these are the line voltages. So that is equal to VL IL cos theta plus 30, VL IL cos theta minus 30. So these two are different with respect to the phase angle. The voltage magnitude is basically equal because of balanced load. Now we have seen this power P1 and P2. Can we use the trigonometric rules of cos A plus minus B and expand the previous equations? So if we expand the previous equations of this power, whatever we have estimated for P1 and P2, and we add the algebraic sum P1 plus P2 to get the total power. So at the end we are getting root 3 VL IL cos theta after expansion of this trigonometric function. Note here we get some constant to cos 30 degree which is equal to root 3. So the total power P1 plus P2 is root 3 VL IL cos theta. Note here in three-phase discussion we have seen that the real power three-phase is equal to root 3 times VL IL cos theta. So that is validating here that the total power that we are measuring using the 2 wattmeter P1 and P2 is nothing but the total three-phase power. Similarly, if we subtract the power P1 minus P2, we are basically getting something of this sort where 2 sin 30 is equal to 1. So this again the derivation we are doing in terms of trigonometric rules of expansion of cosine function. So we are basically getting P2 minus P1 is equal to VL IL sin theta. Here the negative sign is there. So we are changing the position of P1 and P2. So P2 minus P1 is equal to VL IL sin theta. What does it indicate? It indicates that the total reactive power Q2 is equal to root 3 times P2 minus P1. Because we know that reactive power is given by root 3 times VL IL sin theta. So this is your reactive power, and here if I multiply this with root 3 on both the side, I get the reactive power. So that is what the derivation says. It means that if we measure two powers P1 and P2, we are going to get the real power PT and the reactive power QT. So real power PT is nothing but P1 plus P2 and the reactive power QT is equal to root 3 times P2 minus P1. It means only using 2 wattmeter readings we are able to measure the real power and the reactive power of the three-phase system. Once we have obtained the real power and the reactive power of the three-phase system, we can easily get the total apparent power, which is under root of real square plus the imaginary square. So that will equal to your mod of Z, that is the complex number. Hence, in order to determine the power factor which is equal to cos of theta, we need theta first. So theta can be obtained as tan theta. So tan theta is Qt by Pt. The reason is the complex power is given by P plus J times Q. So this is the real power and this is reactive power, and this S is the apparent power or the complex power. So if we take tan theta, then we get this one as Q by P. So here tan theta is Qt by Pt. So that is equal to root 3 times P2 minus P1 by P2 plus P1. So note here that the theta can be estimated if we take tan inverse this side. So if we take tan inverse this side, we can easily estimate theta, and once we estimate theta, the power factor can be obtained as cos theta. So P1 and P2 measurement is sufficient to determine the value of the real power Pt, the reactive power Qt, and the power factor cos theta. So determining tan theta will give me theta, and from theta I can get cos theta, which is equal to the power factor. The two-wattmeter method provides the real power, reactive power, and the power factor also. So it is sufficient using the two-wattmeter method to measure the real power, reactive power, and the power factor. We can also determine the load characteristic. So if P2 is equal to P1, we can say that the load is resistive in nature. If P2 is greater than P1, we can say the load is inductive in nature. And P2 is less than P1, we can say that it is capacitive in nature. The reason is the reactive power Qt is equal to root 3 times P2 minus P1. So if P2 minus P1 is equal to 0, this is possible only when P2 is equal to P1. So it will be resistive in nature. And if P2 is greater than P1, the Qt will be positive. Then it will be inductive in nature. And if Qt is negative, then it is capacitive in nature. So two-wattmeter method cannot be used for power measurement in a three-phase 4-watt system unless the neutral current is 0. So neutral current has to be 0, then only we can use the two-wattmeter method. So the meaning is the system has to be balanced. If the system is not balanced, you will not get the neutral current to be 0. So we stop our discussion here and we'll discuss few problems in the next tutorial series. Thank you for now.